Next up, we have the Simulia team presenting the general lecture. The name of the general lecture is Delivering Sustainable Innovation Using the 3D Experience Platform. And delivering this general lecture are Gregor Judex, Srinivas Thedapalli, and Carl Kuras. Please welcome them on stage. Good luck.
Thank you, Sumans. So this session is about sustainable innovation. It's about the innovation you create for your customers. I mean, most of you are mechanical engineers, and being innovative is one of your daily business. I mean, engineers always have been innovative. Just a 4-hour drive from here is Detroit. There, Henry Ford developed one of the first vehicles with a gasoline engine more than 100 years ago. So he created an impressive invention recognized across the world. But being an innovative car maker today is much more complex. Future cars need to be able to drive autonomously. So you need a lot of innovators from different disciplines to develop a modern car. And a product manager needs to be able to track technologies, actual market trends, customer needs, and regulations to find the best innovation for the next product. But how does he do that? How does he monitor all this information? Well, one way to do that is to use 3D dashboards. Everybody can have his or her own individual dashboard. So a product manager here could track, for example, the actual technology trends for the automotive industry. He could read about the latest safety regulations. And the beauty about using 3D dashboards within the 3D Experience platform for doing so is that you can directly create your requirements, as you can see here on the left-hand side. So deriving requirements from your internal and external data could be the starting point in your development process. And these requirements are now really the basis for your development. And as you from Wärtsilä pointed out earlier, it's very intrinsic to have these requirements closely linked to your products and to your simulations. Now, in the course of this session, we want to show you how you can use 3D Experience and how 3D Experience can support the development of a car. And I know many of you are working in other industries. But I'm very confident that you can easily translate the values we are showing to your business. So we want to start here with the concept phase. There are the challenges to handle different requirements from different disciplines and also manage a lot of design changes. Then in the detailed phase, we are working with external suppliers. And we also want to show you how you can work with the cloud. And then in the validation phase, we really want to check our results against the requirements. So let's have a detailed look at our requirements first. Here I ordered the requirements according to the different stakeholders. So from a customer point of view, the most important requirement may be safety. The car shall have a 5-star rating. And this directly translates into a vehicle performance requirement that we may not want to exceed the maximum deceleration at certain points in the crash. So before I go into more details of the concept phase, let me give you a little bit of a motivation. So as we have seen, safety is very important. So we want to include crashworthiness in our concept phase already. However, to run a realistic crash analysis, we need a car that includes all the various components like the chassis, the wheels, the engine, and so on. But most of these components may not have been developed at that point. So one idea would be to reuse existing components. I want to show you how this works just in a bit. Then, of course, you want to test different variations of your car. So taking into account variants is very important. And last but not least, concept phase is always about changes. This is intrinsic to the concept phase. So the ease of taking them into account is a must. Now let's start with the concept phase. And here the first step will be to create our body in white. And for that I'm using a specific technology called SFE Concept, which is part of the CATIA brand. And the beauty about using SFE Concept is that we can create global parameters so that we can change the overall dimension of the car during the development process. We can also create an associative mesh, and now we can immediately start to run some basic analysis like calculate the stiffness or the eigenfrequency of the body in white. But as I said earlier, our main goal is to run a crash analysis. So now we have to enrich our car with additional components. And since these components are not ready now, we're simply reusing the ones from previous car programs. So here we simply add our chassis, or as in this example, our suspension corner modules. We add an electric motor and maybe other components. And since these have already been used in other simulations, we can also reuse the mesh, which is stored together with those sub-assemblies on the database. Now here I've already loaded the body in white into 3D Experience. Now we want to add the corner modules. So we search for them, and we get 80 hits, and we can narrow them down with 6W tagging. And here I have created a customized tag which will help us to find our component quickly. And then to insert it, I'm just saying insert existing product, and then I'm selecting the corner modules from the other tab. And in the same way, I can add the rear suspension, the wheels, an engine cradle, and also a motor. While this motor is just a placeholder because we do not have an electric motor in our database at the moment. But this placeholder will mimic the stiffness and the mass, and we will exchange it later. Now, another important aspect is configurations, because you want to take into account different variants. For example, the wheels may have an influence in the small overlap impact, so you want to create a variant of that. And how we do that is the following. We store what we call a 150% structure in the system, and then we use filters to select the structure we want to work on. So here I've loaded the 6-spoke wheel, and now we use a predefined filter to switch to the 8-spoke wheel. And now we can start to build a simulation on top of this variant. A key aspect of the solution is the associativity. The associativity between the geometry, the mesh, and the scenarios. The scenarios are really the abacus analysis, the simulations that we set up. So when the geometry is changed, then the mesh can automatically be updated. And in the same way, all the scenarios can be updated as well. So in that case, we have associated an NVH analysis, a stiffness analysis, and various crash analysis to that model. And if you want to see which models are really built on top of your geometry, you go to Business Intelligence, and there on the Simulation tab, you will see that in this case we have 4 models, 4 simulations actually, and then you can access directly these 4 simulations and also access their results. And here we are showing you the visualization of the first crash results with the high-performance visualization engine on the 3D Experience platform. And of course, now you would go into details like verifying specific accelerations at specific points and things like that. So assuming we now ran through several of those analyses, our management may ask us, where are you? What's the actual status? So we can answer that by sharing a 3D dashboard with them, a live dashboard, which updates automatically if new results are available. So here, and we of course want to check against our requirements, so here on the left-hand side we see the row of our requirements. Then the middle column shows the test executions. These are really our abacus analysis that we are about to run. And on the right-hand side you see the validation status. So let's look at some details here. For example, for a side impact, we didn't run these analyses until now. So that's why we are on yellow, not validated. But we are green for the small overlap. Unfortunately, we are still red for the front impact, which directly leads us to the next topic, because now we have to change something. We have to improve our structure. So what kind of improvements can we make? We can modify the geometry. And here I want to remind you of the associativity, because with every geometry change we can immediately update all the models and rerun them easily. Then you can think of tweaking simulation attributes like shell thickness or any kind of loadings. All of those are parameters on the platform so that you can access them also with a process to run them automatically in a loop to see their influence on the results. And finally, you may want to exchange some components. So here we see some of the examples of what kind of changes we could think of to improve our crash behavior. For example, we could change the width of the front frame rail, or maybe we want to change the positioning of the front frame rail. And on the right-hand side, you see how the mesh is automatically updated for every parameter change. And then, while we were working on our simulation scenarios, our colleagues developed the electric motor, which should be used in this car. So now we can exchange the component. So search comes in handy again. So we're simply searching for the newly developed motor and then exchange this with our placeholder. And since we have been using publications, the same publications in both models, all connections are updated automatically so that we can immediately rerun our analysis. Now think of all these parameter changes that you can take into account, like geometry changes or any simulation attributes that you want to change. And if you want to see what is the influence on the results, you may want to run a design of experiment. And since we have process apps built into 3D Experience platform, you can directly access all your models and you can directly access all your parameters, which makes it very easy to set up a design of experiment where you can loop through all those models in parallel. And at the same time, you can write out performance attributes like the comfort, the durability, and the safety that you then want to check against the requirements. So if you've run through that process, you may get out tens or hundreds of results. And then we use results analytics, to validate the outcome. So here on the defined view, we see all the variables, the input variables and output variables of this design of experiment. In the Explore view, we see the ranking of our results, and now we put the first 5 ones into a basket to do some more refined analysis. Then here we can do an objective comparison for these 5 results. And then we can also set the priorities. For example, safety was very important for us, so we increase the priority for the safety, and by that the ranking is changing, so that at the end we ultimately find out that the version 2 is the one that fits our requirements in the best way. So far I've shown you how you can use 3D experience in the concept phase for a car development. But again, I want to emphasize that I'm quite confident that you've found a lot of values that you can translate to your business cases. And if I would rank them, I would say the associativity is really one that is key, because it helps you to increase the throughput of all your different variants that you may want to run. And Andy was talking about the model-based approach, and this model-based approach is really where we derive the associativity from. And then I've shown you how easy it is to reuse existing components and how easy it is to exchange components in a model. And last but not least, I was talking about the verification. And here I've shown you a dashboard, which really is a live dashboard, and this is what Andy was referring to in regards to data-driven. And Carl will talk a little bit more about verification in the third part of this presentation. So, in my opinion, all what I've shown you so far also applies to the detailed phase. However, we want to show you some additional aspects, and this is what Srinivas will take care of. So let me introduce Srinivas on stage and hand over to him.
Thank you, Gregor. So, for the last 15 minutes or so, you have seen how we were able to run numerous simulations in the early conceptual phase. And then we were also quickly able to narrow down our design envelope and pick and choose a design point, which will then be used for the detailed design process. My goal for the next 10 minutes or so is to talk about some of the challenges our customers have been facing for many years as a part of the detailed design process. Let's first get started with some of the challenges here. I'm pretty sure, irrespective of the industry you represent, as well as the size of the company you work for, most of you can appreciate some of these challenges that you face on a day-to-day basis. First and foremost, you all agree with me on the fact that the design cycles within your organizations are becoming shorter and shorter. As a result, there is an enormous amount of pressure on the CAE teams and analysts, which is really you all, to have more throughput and provide your simulation results faster in order to support the product development teams by using all the tools at your disposal. And oftentimes, you're not just working by yourself within your organization in silos, but you are working with your collaborators or partners or suppliers who may be outside your organization. And last but not the least, I'm pretty sure most of you here have at least thought once, thinking, I wish I had more resources to run more simulations. So you need the ability to expand your computational resources, either in the form of software or in the form of hardware. So to solve these challenges, we'll be talking about 2 specific solutions on the 3D Experience platform today. Firstly, as a part of the detailed design process, we'll demonstrate some of the best-in-class generative model build tools available. And for the very first time today, we will be announcing the availability of Abacus on demand on the cloud, powered by the 3D Experience platform. So let's get started here. First thing I do is start with my dashboard. You've seen earlier in the other presentations as well. It's a web-based application where I can access all my requirements, the tasks associated to these requirements, as well as the data that I'll be using in this workflow. Here I have 2 specific requirements. The first one is to perform a detailed NVH analysis on this body model. And the second requirement to actually is work with the supplier in order to make sure that the bracket, which is attaching the door to the body, meets the requirements. I can also use the 3D Play application here in a browser to visualize my model that I'll be using for this workflow. So as a part of the detailed design, this is the model that we will be using for the rest of this workflow. As you can see, this is a pretty detailed body in white model. Let me first separate the front portion of this body in a separate window and look at some of the details. First thing you will notice here is I have already used the CATIA fastening application to create fasteners. One of the unique benefits of using the CATIA fastening application on the 3D Experience platform is I can then reuse the exact same fastener definition and realize them to be my CAE connections. The next step is I'll be using the Simulia automated modeling tool. It quickly launches a dialog where I can pick and choose all the different parts in the subassembly that you can see in the viewport, and then assign a mesh rule. The mesh rule has already been created by an expert and saved on the 3D Experience platform. I can quickly search for this mesh rule and then apply this mesh rule to all these different parts. Material properties and section properties can also be assigned directly through the automated modeler. A green color indicates here that the mesh rule assignment is complete. When you hit OK, you will notice here within a couple of minutes, I'm able to create a very high quality mesh where the mid surfaces are being automatically extracted, shell thicknesses and material properties are also being applied. Everything is done in one shot through the automated modeler on the 3D Experience platform. If you zoom in, you will notice here that this is strictly following my mesh rules, which are in fact coming from the requirements which were originally created and defined. Now this is all great, but oftentimes it's not just one mesh or one model that we are using. As Gregor talked about, there are different CAE teams simultaneously working on the exact CAD geometry. Today, if you look at the way things are done, most of the times, let's imagine there is an NVH team, there is a crash team, and there is a durability team. They make the exact same copy of the geometry, and they are working in silos. With the 3D Experience platform, you never have to do that, because on the exact same product structure, you can create as many mesh representations as possible. In this case, we have 3 different mesh representations, one for the crash, one for the durability, and one for the NVH. And in fact, these 3 meshes have their own independent mesh rules, which were in fact driven by their requirements based on the different attributes. So that when you do it this way, there is no discontinuity in your digital thread. All your data is sitting in one single place. Now that we have these meshes, the next step is to be able to realize this fastener definition. In this case, the unique capability we have is I can simply pick and choose the fastener definition from the CAD product structure and recreate my CAE connections with one click. I have a number of options to realize my CAE connections. In this example, I'll be using a rigid fastener with a distributed coupling option. Literally with a click, my complete CAE fastener definition is created on the fly. The other huge advantage of using the data-based and model-based approach on the 3D Experience platform is, if my fastener definition on the CAD side is changed, with one click, I can update my CAE fastener definition. So on the exact same model, we have now scaled up to the complete body model. Multiple users were simultaneously logged in into the 3D Experience platform, and we were able to create a complete body in white mesh, including all the 3 different meshes for 3 different attributes, namely NVH, crash, and durability. So let's take a look at one of those results. This is looking at some of the modes of vibration for a complete body model. And we are making sure that the fastener definition is in fact correct, because there is no separation in your geometry. So this is all great. This is being done in-house. But oftentimes, as I discussed earlier, most of you are working with your other teams, either within your organization or outside your organization. In this particular workflow, what we want to demonstrate is how you can easily work with your suppliers. One of the requirements to the suppliers can be who is providing us the door model is to use CATIA. In this case, the customer or supplier can be using CATIA, or in fact, you can use any other CAD geometry. But of course, one specific requirement for this supplier was to use an abacus model, because that's the solver that the OEM trusts and uses in-house. and has been using that for many years. But a lot of small and medium-sized customers have their own IT challenges that they have to deal with, especially when you're required to provide an Abacus model in a very short span of time. Some of the challenges include not having a dedicated Abacus license to do simulations day in and day out, or even if you do, your tokens might be insufficient. And this is quite common with most of you here. The other challenge is, even if you have tokens, you may or may not have the necessary hardware to run your simulations on demand. And last but not the least, you need to have the IT personnel to support all your simulation capabilities. We believe the answer to all these problems is access to Abacus on demand, powered by the 3DEXPERIENCE platform on the cloud. So to demonstrate that, let me put myself in the shoes of a supplier and show how I can access Abacus on demand. The first thing that I do here is, again, open a web browser and log in into the 3DEXPERIENCE platform. I can access my dashboard, which has been discussed over and over in the past few minutes. I navigate to the compass and select the Abacus Steady application. As you can notice, everything I'll be using here is done completely through a browser. The first step I do is I need to perform a door sag analysis to look at the stresses in my bracket. So I go ahead and create a project space and give it a name. The next step is to go ahead and upload my Abacus input file to the cloud. I can use Abacus CAE or, in fact, any third-party preprocessor. There's no limitation in terms of where I'm getting my Abacus input file. Once I upload my Abacus input file, the next part of this workflow is to use Abacus Standard Solver to perform a door sag analysis. And this is where you use your typical Abacus commands. You create a job, and then select the input file, and also use any additional input files if needed. Within the options, you will notice here that the location, you will be choosing cloud. So this is where you'll be running the job on the Dassault Systems hardware infrastructure. With a simple performance slider, you can pick and choose the number of cores you want to use for this particular simulation. We'll be using 4 cores in this example. You also have the ability to save the desired Abacus output files as needed. When you hit OK, you will notice here within a couple of seconds, your Abacus job starts and is being fired off on a remote cluster in one of the DS data centers. You navigate back to the project space. You will notice this is where you find all your typical Abacus output files that you're used to seeing. You can tail the status of a specific job. In this case, we are looking at the status file, which indicates the job has been completed. A results file is automatically created, which I can then use to post-process this job. I go to the compass and select the 3D Play application. It's a lightweight visualization application within a browser where I can use this application and perform a post-processing. In this case, I am specifically interested in looking at the stresses in my bracket that is going to attach my door to the body model. I can quickly navigate and make sure that the stresses are, in fact, meeting my requirements. You can even make annotations within this 3D Play application. One of the other unique capabilities of the 3DEXPERIENCE platform is I can directly share these results to anyone who has access to this 3DEXPERIENCE platform, directly from the dashboard. Here, I'll be communicating some of these results back to the OEM, who has, in fact, asked me to perform the specific workflow. All you need to do is put in an email and then put in a specific message that you want to review these results with the OEM. Let me put now myself back in the shoes of the OEM. All I do is just click on the link that I have received in my email. This directly navigates me to the exact same 3DEXPERIENCE platform that the supplier is using. No more emails, no more PowerPoints. In this case, once I log in into the platform, I see a notification that the results have been waiting for me from the supplier. When you say OK, you will notice that you can directly navigate to the exact same results that the supplier was looking a couple of seconds ago. This is, again, the unique capability of the 3DEXPERIENCE platform where you're not moving the data back and forth. I can review these results myself and suggest any changes if necessary. In this particular case, I'm quite happy with these results. So let me quickly recap what you have seen in the last 10+ minutes. First and foremost, we have talked about some of the generative model build capabilities on the platform, starting all the way from a detailed body-in-white geometry, and then using the CATIA fastening application to create fasteners, and then use the exact fastener definition and realize them to be CAE connections literally with one click. We have also seen the ability to create as many finite element representations as needed on the exact same product structure, so there's no discontinuity in your digital thread. Secondly, for the very first time today, we are announcing the availability of Abacus On Demand, powered by the 3D Experience platform on the cloud. And we are now providing on-demand hardware as well as software licensing, which you all have been asking for many, many years. And last but not the least, we believe we are now providing you all scalable on-premises as well as on-the-cloud simulation options, where we are now providing faster access to infrastructure, thereby improving your overall IT efficiency. Cloud brings you the ability for a much bigger geographic reach. No matter where you are, you can access to the 3D Experience platform and review your results. And ultimately, all these will enable you all to bring your products faster to market. While I have been discussing you about some of the capabilities as a part of the detailed design process, I'm going to now invite my colleague Carl, who will then talk about the validation aspect of it. Thank you very much.
Thank you, Srinivas. So my colleagues have shown how we can place simulation at the heart of innovation throughout the design process, from concept design all the way through to detailed design. And so my task for the next few minutes is really to show how we can close the loop and ensure how we validate those design points. As we saw in the keynote from Wärtsilä, management of the testing that we use to validate our key performance indicators of design is very important, and quite a complex task. We may have a number of key performance indicators that we're testing against. Our tests will be a combination of both physical tests and virtual tests that will complement each other. We may validate our simulations with physical test data, or we may actually enrich those tests, those virtual tests, with road load data and so on. And so management of both of these data sets poses some key challenges for us. Ideally, we would like to manage both the physical test data and the virtual test data in a consistent way, making sure that it's easily traceable and interchangeable, and we can validate against both physical and virtual tests. We also need to ensure that our test engineers are following the best test procedures and methods. Of course, we want to track that our tests are validated against the requirements they're testing to support. And we want to be able to share the results of our tests as soon as possible with key stakeholders in the project. To get a scale of the problem or the data management exercise when managing tests, let's have a look at a small subset of the testing requirements for our body-in-white model. For the durability requirements, we may run a number of simulations to test the stiffness, the strength, the fatigue life, and so on. And we'll have some physical tests that support those virtual tests. During our complete design cycle, we may run a number of different variants of our vehicle. And again, that will be complemented by physical tests. If we scale the scope of that problem to safety requirements and NVH requirements, we can start to see the number of tests that we have to perform and manage throughout the design cycle. And a key challenge here is what happens if something changes, if there's a design change or a requirements change. How do we quickly and efficiently identify which of these test procedures are the most important and critical and need to be rerun? And can we manage that process to rerun them efficiently? So I'll be talking over the next few minutes about some of the key technologies we have to manage this process. The first thing I'm going to show is how we can use the model-based approach on the 3D Experience platform to contain both the physical test data and the virtual test data in a consistent way. Within the 3D Experience platform, I can create engineering templates which will allow me to instantiate models, both physical models and finite element models of our sensors, for example. In this case, I've created a template of a number of different strain gauges that I can position on my digital model. The template here not only captures the geometry of the strain gauge, but also a finite element representation. In this case, I'm representing the strain gauge with a combination of beam elements, but you could use any fidelity of finite element model within your template to represent that. As well as the finite element representation, we can store within this model a number of key parameters which will allow us to store information, such as the maximum strain from the physical tests or the virtual tests, and attach it to our digital model, making it available and traceable to the users. And of course, we can attach documents to our digital models as well. So if we have some raw data that we need to attach and make available in our digital landscape, we can make that available to all the users to access very easily. Once these engineering templates are created, I can instance them on my full assembly for the vehicle. I can do this very easily and nicely within the platform. So I've created a catalog of all of the templates of the different strain gauge sensors that I've built on the platform, and I can then instantiate these templates very easily to include them in a particular assembly. You can see in the interface here I'm prompted just for a couple of key inputs to build this sensor: the location of the sensor and also the surface that it sits on. I've also exposed a couple of parameters which will allow me to orient the sensor in space to align it with the key stress and strain directions that I might be interested in measuring in my physical and virtual tests. So instantiation of these sensors is very easy, and then they're stored with the digital model and traceable. And I can repeat this process for an entire array of strain gauges that I might need to use for different load cases and so on. Here I'm zooming in to see some of the array of strain gauges and different strain gauge types that I'm using for my various tests. As well as being able to store and manage the physical test data with the virtual test data, I mentioned that we also need to make sure that the test engineers follow the procedures and best practice methods when they're carrying out the tests. And we can do this using our process management applications. Our application called Process Composer allows us to capture all of the steps required to carry out a test and manage all of the data produced. So for example, for my stiffness calculation in Abacus, I can capture all of the activities required to complete that task. I can download instruction documents informing the user how to complete the test. I can exchange attributes. I can read attributes from the data, and I can assign attributes to the data. And this is important, and we'll see later how this helps us make it more traceable. I can run activities which will allow me to copy data objects from the database and reuse them, such as a simulation template, to enable me to just use a simulation that maybe Srinivas or his colleagues have built. I can run interactive tasks which will allow the user then to take that copied data and make edits to build the new load case. And my final activity will then be to run the simulation and manage the simulation results on the database. Once I've deployed my process, I can access it through a browser. And you can see through the browser interface all of the inputs and outputs associated with this simulation template. So here I can access directly all of the key inputs, and in fact I can navigate to the instruction documents that the user will need to follow in order to perform this task. As well as the key inputs and outputs, I mentioned that we can also assign attributes to this simulation process. So I can choose the load case that I'm running, I can choose the vehicle program that I'm working on, and so on. And this allows me to make the simulation process much more traceable in the future to make sure that we can find it in the database. So now going to run the simulation process. And again, I can launch this directly through the browser. Since there's an interactive activity in this process, what will happen is we will launch the rich client application with the correct data already loaded. And the end user can then access that simulation template, make any necessary changes to the template to build the new load case, and save that simulation. Once that's done, we will run the simulation automatically and store the results. And so again, through my simulation process, I can access directly the results and review those. I can create any number of these simulation engineering templates or process templates to perform physical tests and virtual tests. So in this case, I've captured the process for loading and managing physical test data. And the second activity I'm showing here is extracting the values from the physical test data and the virtual test data and combining those into a report to validate the differences. Each time we run a simulation process, we'll see on the left-hand side of the screen here all of the times a simulation process has been activated and accessed and run. If I want to filter the results and see only the simulation processes I'm interested in, I can use the 6W tags. And again, linking back to those attributes that I assigned, I can easily find all of the simulation processes that relate to the torsion test case for my body in white, and for the particular vehicle program that I'm working on. So it gives me full traceability of the individual simulation processes that are of interest. And I can access that information. For my V+R results management process here, I'm now going to create the report which will compare the physical test data and the virtual test data. So the simulation process is reading the detailed strain gauge results from those tests. And we can see here now that that report has been created, and I can access it through the browser. Populated in the report, we can see that we've automatically assigned those attributes. So we've populated the test case that we've run, all of the strain gauge information, and how the physical tests matches to the virtual tests or not in some of these particular cases. The next thing I want to talk about is how we manage the executions of those tests and validate them against the specific requirements that we've set for our products. As Juho showed in his keynote, the requirements capture capability on the 3D Experience platform allows us to capture not only the requirements, but a set of test cases that we use to validate those requirements. And for each test case, we can actually assign a number of these process templates that we create using Process Composer. And so these are the processes that we use to test our requirements. For each test case, we can run this a number of times during the life cycle. So each time we execute a test, we'll instantiate a test execution object. And for each execution, this will store the number of times that we've run our simulation templates to capture those results. So for example, you can see that the top template there has been instantiated each time we've run a test execution. Looking at how that looks in our interface, we can see all of the simulation, all of the requirements for our product, and we can link directly to those requirements. So in this case, to the torsional stiffness. The hyperlink allows me then to link directly to the torsion test case that we use to validate that requirement. And the test case provides us some really valuable information and traceability of each time we've run and executed a test. So down at the bottom here, we can see all of the simulation process templates that we use to validate that test. So we can trace very quickly which tests we need to rerun if that requirement changes. The Test Executions tab allows us to see all the times that we've executed that simulation process and see how the evolution of the requirement has moved. And the parameters show us how those key performance indicators and how well we're meeting those key performance indicators. If I select a particular parameter value, I can trace how that key performance indicator has evolved with our design. So we can see how well it's meeting our targets as we change the design process and execute further tests. For the test engineer, we provide full traceability, so they get a 360-degree view of their product, both from the requirements and the requirement targets, all the way down to the physical product and all of the simulations associated with that physical product. Using the business intelligence applications, we can very quickly navigate to all of the simulations that support this product. So in the event that a requirement changes or a product changes, we can see directly which simulation processes and which simulations we need to rerun. Finally, once we've performed all these tests, we want to be able to share that information with the key stakeholders. And we will do that using the 3D dashboard. Here I've created an interactive report, a web-based report, using the 3D dashboard. I've created a plot which shows the location of all of the sensors on my digital model. And I've been able to use the dashboard applications to publish the reports for the virtual and real tests and how they match with each other. As we've shown previously, the 3D dashboard is live data, so this will be shared in real time and updated as the tests are reperformed. So let me just recap some of the benefits that I've shown over the last few minutes. I've shown how the 3D Experience platform allows us to capture and manage both physical test data and virtual test data with the digital model. I've shown how we can ensure that our test engineers follow best practices and methods using our process management applications. And I've shown how we can manage and track all of the tests that we perform against the requirements that they're testing against. And how we can share the results with all of the key program stakeholders in real time. If you're interested to find out some more about our process management applications, then I'd be happy to see you at the technology update that we're running tomorrow morning. So to recap, just to have a quick look at the technology that we've demonstrated to you over the last 40 minutes or so. Gregor started the presentation showing 3D dashboard, how we can start to understand the requirements of our products and understand what we need to do by mining the data available to us, both from customer forums, it could be from warranty reports, it could be from real load data from sensors on your car. We can mine all of that information and extract it to define our early requirements. He then showed how the synergy between CATIA and Simulia allows us to perform many different designs and simulations on our early concept phase designs and really narrow down the best concepts to move forward. And finally, he showed our results analytics application to do trade-off studies against those different concepts and to choose the best concepts to move forward with. Srinivas showed our multi-physics applications, again to show how at the detailed design phase we can use the 3D Experience platform to run and improve the throughput of your simulations to improve the detailed designs. And he showed how we can access Abacus, both in terms of hardware and software resources on the cloud. And finally, I showed how we can manage the test and validation process using our process management applications available on the platform, and how we can share the results of those applications and tests on our 3D dashboard. With that, I'd like to thank you for your attention. I hope you enjoyed our presentation, and I look forward to meeting you for the rest of the conference. Thank you very much.